In this video, we're going to look at an example of how we can use constant pressure calorimetry to calculate the enthalpy of a reaction that takes place in solution. So we're given a lot of information here. We're given the amounts of the two reactants. We're told what the temperature change is. We're told that we're going to assume the density of our solutions is the same as that of water, and that the specific heat capacity is the same as that of water. And what they want us to calculate is we want to know what is the enthalpy of reaction for this reaction as it's written in kilojoules. So the way we're going to calculate this is we're going to use the law of conservation of energy. The law of conservation of energy tells us that the heat gained by the surroundings is equal to the negative of the heat lost by the system. Or in this case, the system is the chemical reaction. Now, whenever we have solutions, the vast majority of the solution is the solvent. And it's the solute that is actually reacting. That's the system. The vast majority of the water is the surroundings. So this temperature change, we're going to assume is the surroundings. So we're going to calculate the Q for the surroundings, and then that will allow us to determine the Q for the reaction. And then the enthalpy of the reaction is going to be the heat given off by the reaction divided by the moles of the limiting reagent. Now in this case, I have exactly the same number of moles of HCl and NaOH. And because they react in a 1-to-1 ratio, they are both the limiting reagent. So I'm going to have the same numbers of both, so I can use either the HCl or the NaOH when I calculate the moles. So to calculate the Q for the surroundings, I'm going to use that Q is equal to mass times specific heat times the change in temperature. And in this case, my mass, I have 100 milliliters of solution after I mix the hydrochloric acid solution with the sodium hydroxide solution. We're assuming the density is 1 gram per milliliter. So if I have 100 milliliters, I have 100 grams. I'll multiply that by the specific heat, and then the change in temperature. All right, and I should have included my units on here. The specific heat has units of joules per gram times degrees Celsius. Delta T is going to be in degrees Celsius, so our grams will cancel, our degrees Celsius will cancel, and our heat will be in joules as we would expect. And so when I do that, I get the Q for the surroundings is 2803 joules. All right, but I know that the heat for the reaction is going to be the same magnitude, but opposite in sign. So that means that Q reaction is going to be minus 2803 joules. All right, so now to get the enthalpy, I just divide the heat for the reaction by the moles of the limiting reagent. So I need this moles of limiting reagent. As we said, the amount of HCl and NaOH is the same, so I can use either one. I'll go ahead and use HCl. So I know that the molarity is moles over volume. So that means that moles is equal to molarity times the volume. So my moles of HCl is 1 mole per liter. 50 milliliters, I'll need to divide that by 1,000 to get it into liters. So that is 0.0500 liters. So my moles are 0.0500 moles. So let me scroll up here a bit. So now my delta H for the reaction is going to be minus 2803 joules divided by 0.0500 moles. So that comes out to be negative 56.1 kilojoules per mole, and this is really HCl. So I actually disagree with how the book does the units here, but I'm going to follow their convention for consistency. So the last step that we need to do is we need to take into account the stoichiometric coefficients of the chemical reaction. And so because 1 mole of HCl reacts with 1 mole of NaOH in this balanced chemical reaction, it's actually a little bit easier. If these coefficients had been different, we'd have had to be a little bit more careful. But the answer should just be in kilojoules. The way we get from kilojoules per mole to kilojoules is that we're going to use that 1 mole of HCl, and I got that 1 from the coefficient of the equation, is what's going to take place in the reaction. And so if this coefficient had been anything but 1, I would use that number down here. But I have minus 56.1 kilojoules per mole of HCl, and that's times 1 mole of HCl in the reaction. So it ends up being minus 56.1 kilojoules. And so that's how the book gets rid of the moles in the kilojoules per mole.